Hey, Robert.
Hi.
Hi, thank you for attending. I think it might be just me, but in the meeting, it's going to be recorded because, this is uh, different schedule time. So it's typically every 2 weeks. So this is like one of these odd weeks. So then we might have less participation. But in any case, it'd be great to hear about the TFX project. And the meeting gets recorded and gets posted on the CNCF TAG-Runtime channel, so YouTube channel.
Okay. Well, should we wait a few minutes to see if more people show up?
Yeah, let's wait 2 or 3 minutes.
Where are you located?
I'm in the Bay Area, in the San
Oh, you
Mateo.
are.
Yeah.
Oh, okay. Yeah, me too.
What part of the Bay Area?
San Jose.
Okay. Yeah. I'm in San Mateo. So
Yeah.
cool. We have this meeting minutes here, so I'm gonna go ahead and add you as a attendee. I'll take some notes. There you go. Yeah, I think you can get started. So, do you have some slides or something to share?
Yeah. Okay. Let me share here. Come on.
We don't have to go the full hour. Depending on.
Okay. Well, I'll just go through what I've got, and then if you have questions or anything, we can do that.
Sounds good.
You can see my screen.
Yeah, yeah.
Okay, so the topic is on TFX portability,
Hmm.
um, and we'll get into why that's important.
Hmm.
Um, so if I can get my, there we go. So machine learning pipelines, the tasks involved in machine learning fall naturally. It's a series of tasks. So if you work in ML, then you're familiar with this like flow. You start with ingesting your data, and then you do some validation and try to study your data and understand it. Then you do feature engineering to change your data to make it train better, and then validate what you've trained. Well, then you train your model, and then you validate it, and then if it turns out to be good, which it does, some percentage of the time, but not always, then you push it to some serving target or deployment target, and that's the flow. In general, there's, of course, a lot more complexity there, but in general, that's the flow. So TFX mirrors that flow typically, although it doesn't have to. This is kind of the canonical pipeline that you start out with TFX. There's a lot you can do to change this with branching and adding custom components and what have you. There's a series of open source libraries that support key parts of the ML process, like validating data and transforming it and training the model, of course. and doing really some deep analysis of model performance, which we don't really get into in this presentation, but it's a very important topic in the field.
Mhm.
And then, of course, serving. Um, so this is another look at TFX that shows really the dependencies and the flow through the pipeline. And actually, there's two pipelines shown here.
Mhm.
The one in orange is a training pipeline, and the one in green is an inference pipeline where we're using a trained model to generate predictions in a batch setting. Um, Also, you can see on the right from the training pipeline, we're deploying to any of a number of different targets. So it could be TensorFlow serving or some other serving infrastructure if you're running like in a cluster, what have you.
Mhm.
TensorFlow Lite if you're running in a mobile app, TensorFlow JS if you're running in a web browser, or some model repository like TensorFlow Hub.
Mhm.
Um, the key thing about portability is because of the way we put things together with TFX, you can run TFX just about anywhere. So what does that mean? Well, in terms of execution, I can run TFX in a Colab or any Jupyter notebook, just the entire pipeline by itself, just running in a notebook, which is very familiar and very useful for data scientists and ML engineers. I can also just run it on my laptop, which I do, frequently when I'm developing pipelines, and use an IDE if I need to or what have you. I can run the whole thing just on my laptop. I can run it in a Kubernetes, containerized environment. When I take that pipeline that I've developed in a notebook, I can move it up to a Kubernetes cluster and run it. And I can run it in Vertex AI, which you may have heard about. It's a recent offering that Google announced to do. It's a managed service for running ML on the cloud, including a pipeline infrastructure, Vertex AI pipelines.
Mhm.
So that's just in terms of execution. For orchestration of the pipeline, which is important for any sort of pipeline architecture, we're also portable. So in a notebook environment, I can run. I don't have to, but I could just run in and use Python as an orchestrator. So for a lot of Python developers, that's very familiar and very flexible. I can also run in orchestrators, more dedicated orchestrators like Apache Airflow or Kubeflow.
Mhm.
Or some arbitrary orchestrator that I want to add. So there's portability there too. And in terms of the processing itself, so as we're crunching through this data, where is that crunching happening? Where are the CPU and compute resources to do that crunching? Well, it could just be on my laptop, which if I'm running on my laptop, that's where it's going to be. Or I could stand up a Spark cluster or leverage a Spark cluster that's already there. Or I could use a Flink cluster, or as a managed service, I could use Cloud Dataflow, or you could extend this to similar cloud services on Azure or AWS. So that's what we mean by portability. At three different levels, really. It's portable across environments.
Mhm.
So why is that important? Well, the basic philosophy is that we really want to meet the user's needs instead of requiring them to meet our needs. And portability really allows us to do that. It means that as a user, I can choose an execution environment which works best for me, either just for the moment, I want to try to get things done on my laptop, or as an organization because I want to run a Flink cluster instead of a Spark cluster, for example.
Mhm.
Um, Also, in terms of orchestrators, you have infrastructure teams who are more comfortable with one orchestrator than another. Um, Largely, because that's what they have. They're maintaining it for other things. They're familiar with it. They have the skill set for it, or they like features that it supports. different distributed processing frameworks. Again, if and this becomes important, especially when we have different teams, maybe from acquisitions or geographies or what have you, they could be running different clusters for whatever reason, and they can move that pipeline between those clusters. And even languages to some extent. Python is the main language you work with in TensorFlow and TFX. But in fact, you can also, by creating containerized components, and I'll talk about what components are,
Mhm.
you can in fact run whatever language inside that component, as long as you maintain the contract for the inputs and outputs. So teams or business units could be doing very different things, either as an organization or at different times. And that portability allows them to move between those different options and environments. So again, back to TFX, this is sort of the hello world of TFX. Those things in orange and in green there, the main ones, those boxes, those are components.
Mhm.
So I'm going to talk about what components are, and it's all kind of backed in this metadata store that I'll also talk about.
If questions, so in terms of you can use Airflow or Kubeflow as the orchestrator, but so there's no overlap with Kubeflow as far as this diagram shows, right? So as I understand, Kubeflow also has some other mechanism to train data or to do steps in the pipeline.
Mm. So there is Kubeflow pipelines, which in fact is when I talk about Kubeflow, that's what I mean is Kubeflow pipelines.
Okay.
So this is running on top. When we run in a Kubernetes environment, this is running on top of Kubeflow pipelines.
Got it. So, and I guess, and there's some other components in Kubeflow that may be equivalent to TensorFlow extended has, or yeah. So, I mean, I don't know all the different components of Kubeflow. So, I mean, I'm asking for out of curiosity.
There's overlap. I mean, since they both implement pipelines, you could, do a comparison that way. TFX is much more oriented towards ML pipelines, so doing machine learning workloads.
Got it. Yeah.
Yeah.
Cool.
Okay. So components. I'll go into some detail about what a component is. So the tasks, again, are expressed in the pipeline as components. So there's a component for ingesting data. There's a component for doing data validation and analysis, and so forth. Those tasks map to components. That's backed by ML metadata, which I'll talk about in a second. There's actually pipeline nodes. So in fact, components are a particular type of pipeline node. But and we'll get into that a little bit more too. But components are the main pipeline nodes that you work with. There's some others as well. One of the important ones that is not a component is a resolver. And a resolver reaches into ML metadata and allows you to do queries against the data that you have and pull out data artifacts that you're going to use in a component. So resolvers they're not a component, they're a pipeline node, but they become fairly important in some scenarios. Actually, quite a few scenarios, but you could work without them as well. So what makes a component? Well, it's a driver executor publisher pattern. The driver pulls the input into the component and handles the job execution. including things like parameters and so forth. The executor is really where the work of the component is done. So that's where the different tasks really differentiate different components. And the publisher takes the result and puts it into ML metadata. So that's going to update the graph in ML metadata that expresses your pipeline run. And we'll talk about that in a second.
Mhm.
So another look at this, the component is taking its input as artifacts from ML metadata. It does what it's going to do. It has a config as well. And then it puts its results back into metadata. And it does that over channels. So channels are just, you could think of them as a helper class, just to kind of abstract the operations of reading and writing from metadata. But in fact, the way that that's abstracted, you're really not even worrying about metadata at all. You're just reading input and writing output. So that's how components communicate with each other. And that's how data flows through the pipeline. So an upstream component generates a result. Those are artifacts that flow into metadata and then are retrieved as dependencies for the next component downstream and so forth. So that's how data flows through the pipeline. One of the pipeline nodes that we have is the importer node, and it's sort of a special node. It's used if you need to pull arbitrary data into a pipeline for some reason. You just need to supply, the URI that you're going to pull it from and the artifact type, because again, this is going to be inserted into metadata, and then, presumably used by a component for something. That's why you would use this. And the result.
This importer node is a physical node. Is it like a server or something, or it could be a container or something? Or
No, this is all software.
okay.
Let's see. When you run in a containerized environment, I believe this is containerized separately.
Mm-hmm.
Yeah.
Okay.
Um,
So this is the sample Python code here at the bottom of this. So and then it could be run somewhere basically. Okay.
right. So if it's being run in a container, that actually happens automatically when you run. You're not worrying about containerizing it yourself.
Okay.
So you're not setting up a Docker file for this or anything like that.
Got it.
So resolver node I mentioned earlier, resolver allows you to do queries into metadata. So like if you want the latest outputs from the example gen component and you want the latest 5, you can do this kind of query, which is useful in some scenarios. For the distributed processing portion of this, so let's take an example. We have a component called statistics gen. Statistics gen generates the statistics for all of the features in your data set. Well, your data set could be, half a petabyte. So you're not going to do that on one CPU, or if you try, you're going to wait a long time.
Right.
So you need containerized processing, or I'm sorry, distributed processing. So your component, your statistics gen component, is going to kick off a job, and it's going to use Apache Beam to do that, and it's going to run it on whatever cluster you've stood up. So there's a number of different languages that are supported by Beam in different, and they have SDKs for each language. So Beam sits in the middle between your SDK and your cluster, and you issue commands or you create pipelines really in the Apache Beam SDK with Apache Beam abstractions like sum per key. So the operations and collections. Those are issued into Beam. Beam translates that into the native SDK for whatever target you're looking at, and a result is generated. So that's how a component reaches into a distributed cluster, does a whole bunch of processing, and gets a result back.
Mhm.
So to author components, there's really three ways to do this when you're authoring a custom component. We have a whole set of standard components that come, just when you do pip install. So the basic things like trainer and transform and evaluator and so forth. But you can do a lot with custom components as well, and people often have a need for that. And there's three ways to create those. A Python function, which is very simple, and we'll look at that. A full custom component, if you need complete control over it, or a containerized component, which again is where, suppose you want to run a component in Java, maybe because you have a lot of code in Java, you can do that in a containerized component. So for a Python-based function-based component, all you're going to do is decorate. You have a Python function. You're going to decorate it with a decorator here and some annotations on the arguments, and boom, you're done. Bob's your uncle. So so that's usually the kind of the first level that people start with and work in, unless they need more. For a containerized component, it's still pretty simple. So we have a wrapper called create container component. You're going to take the arguments and again you're going to sort of define those as artifacts. You're going to have to identify the image you're starting with, of course, and the command that you want to run when you start the container. But pretty straightforward. So again, this is what you end up with. Those things we're talking about, those components are, these things in orange here, or in a inference pipeline. I have them in green. So defining the pipelines with components is done by using the TFX SDK. And that, again, typically mirrors the ML training workflow. But, in fact, you could use this workflow or the pipeline for whatever works for you. But most people are using it for that. So the order of execution is defined by data dependencies. So, and there's a DAG runner that is specific to each orchestrator. So there's a DAG runner for Airflow, there's a DAG runner for Kubeflow, actually Kubeflow pipelines, there's a DAG runner for Vertex, and there's a DAG runner for just locally running in a notebook.
Mm-hmm.
And this is what it looks like. So this is the code to generate a pipeline. And I only have two components here just to show how the dependencies work. So example gen is the first component. Typically, it's going to ingest the data into the pipeline. So the data root here is important for that. That's where it's going to look, in this case, for a CSV file.
Mm-hmm.
Statistics gen is going to depend on the outputs, actually the examples portion of the output from example gen, and that's the data dependency it's going to have for that component, and so forth. So that's how you define a pipeline. That's really.
What about the metadata? So metadata is stored somewhere, or
We'll get to that in a bit.
okay.
So this SDK and Python is expressing a DSL. It's expressing the semantics of a DSL. So the DSL defines how data flows through a TFX pipeline. It defines when the components consume the data and execute. It expresses things like conditional control flow and sub pipelines, which we haven't talked about, but you could think of as an abstraction, a pipeline within a pipeline. Mm-hmm. And those semantics are expressed with the TFX SDK. So that gives us portability. And there's an IR, an intermediate representation, that is used as a separation layer between the DSL and the target orchestrator and environment. So the IR, the intermediate representation, is a declarative representation of a particular pipeline. So that enables portability to arbitrary execution environments and orchestrators. And it expresses the semantics that we just talked about in the DSL and the SDK. And it mirrors the MLMD or ML metadata data model, which we'll talk about in a second.
Mhm.
So the data model, or you could look at this as either the data model for the IR or for the metadata, because they're mirrors of each other. It has vertices, and those vertices are artifacts. So an artifact is an output of a node in a TFX pipeline, and it can potentially be fed into another node as input. Or it could be just like a saved model, for example. It could just be the results of the pipeline. Executions of nodes, or you might think of components, an execution records the execution of that node. So that's also a vertex in the graph of the data model. And the context describes, well, really at an abstract level, it's a grouping of workflow elements. Typically, it's a pipeline run. So within a run of a pipeline, those would all be grouped into a context. The edges of that graph are events. So events link artifacts with an execution. Remember, so the artifact was the result of a component. The execution was the execution of that pipeline node. And that includes the type of the event, the key of the input or output artifact, because these are like dictionaries, and the index, because some of those items are actually lists of things, so that we need the index into that list. The attribution links the artifact to a context. So that's going to link, in most cases, an artifact, a result of a component run, with the pipeline run context for where it was generated. And there's an association that links the execution of individual nodes with that context as well. So here's an example. We have an execution here of some node, and it produces an output, which is an artifact. This edge here is an event, and these are attributions or associations, depending on which one you're talking about, with a context, the pipeline run. Mm-hmm. So this is what the IR looks like. It's a protobuf. You typically don't see this. It's usually not materialized. So usually this is just in memory, and it's passed down. We'll talk in a second how this gets translated. But if you were to look at it, if you wanted to look at it, this is what it would look like. Mm-hmm. There are DAG runners. So a DAG is a directed acyclic graph or pipeline. And each DAG runner is specific to a particular orchestrator. Because they're going to handle really taking that abstract representation and making it concrete for a particular orchestrator. They're going to compile that pipeline to the IR, the intermediate representation, and then they're going to translate that IR into an orchestrator-specific representation. And that instructs, then they're going to instruct the orchestrator to execute the pipeline. Now, actually, this is a little bit. Usually this is what happens, although you can actually separate the compilation from triggering the execution. But typically you don't. Typically this is the flow. There's also a component launcher. So a component launcher just executes each node. So that's responsible for executing each node in your graph. And it also handles caching, because if the inputs to a pipeline node haven't changed, then we don't need to rerun that pipeline node. We already have the result in cache. And remember, we could be talking about petabytes of data. So it could take quite a bit of resources and time to run that node. So if we don't have to, let's not. It handles things like conditional control flow, like have the conditions been met. It handles I/O resolution into, well, depending on the node, it could be reaching into some file store or what have you, or it could just be with metadata. And there's 4 launchers currently. There's an in-process launcher that we use when you like run on your laptop. There's a pure Docker launcher when you're running that way. There's a Kubernetes launcher and Borg. Borg is the internal. You could think of it as the Google internal version of Kubernetes. It's not exactly that, but it's close.
So how did question? So how does it handle the petabytes of data in the cache? I mean, do you need like a lot of physical memory to handle, like if you're, or is it stored in somewhere on disk or?
Didn't actually talk about that, but so metadata is there's a database that stores the metadata graph, or actually collection of metadata graphs, because you're going to run a lot of different pipelines. The actual payloads for the actual payloads for any artifact that is beyond just the metadata itself is kept in a block store somewhere. So
Okay.
there's a URI in the metadata that points to the destination in a block store. Could be a file system, or could be like a bucket on GCS or what have you.
Yeah.
That's where that data lives. When it's supplied to a component, they're going to use that URI to go grab that data.
I see. But it may not actually be fast. It depends on the storage, right?
Yeah, right. Just like everything else.
Yeah. Okay.
Yeah.
Cool.
Yeah. So MO metadata is capturing the component outputs. It's supplying the component inputs as well. It mirrors the IR data model. So those things are basically the same. It manages data as it flows through the pipeline. And it records pipeline executions and intermediate results, which can be really important for analysis, and including things like regulatory requirements and legal reasons. You may be sued for some reason or what have you. Having all that, we call it lineage of all those artifacts and results, you can go back and analyze. That becomes important. And then there's orchestration. So orchestrators handle the running of a pipeline. So they watch for components that are ready to run, and they monitor for successful completion of the pipeline, or actually for each pipeline node. And that's how it works. So here's some references. If you'd like some more detail, especially these RFCs have a lot more detail on some of this stuff, like the DSL semantics and the IR. And of course, our website has a lot of information on and examples and user guide and what have you. So that's my talk.
Cool. Thank you. Does the website have any use cases, or like who do you currently have any users besides Google now, or that's in progress?
We have tons of users. Yeah.
Okay.
Yeah. TFX is the leader in production ML. So Production ML, I didn't really talk about. Let me step back a second and
Mhm.
people doing data science or machine learning or AI, when they're doing research, a lot of this isn't really something that they work with a lot of the time.
Mhm.
Although in many cases it really should be, but often they're just kind of cobbling things together in sort of an ad hoc way in order to do some research and publish a paper and move forward, because what they're really focusing on is their research. In
Mhm.
academia it's similar. Maybe you're trying to complete a class assignment or what have you. When you move to production, meaning you're going to use machine learning in a product or service, then it becomes important to have a process and an infrastructure that is appropriate for a product or service. And we've spent years designing those things
Mhm.
for all kinds of products and services. And there's uh, best practices, things like CI/CD that the people have evolved and know and love.
Yeah.
This kind of ML pipeline is what people use when they're creating a product or service with machine learning, because it sets up a repeatable and robust and traceable and scalable infrastructure for them that they can then use because you're not going to just train a model once.
Mhm.
Um, People outside of ML, I think, often don't realize this.
Yeah, it's a continuous training, right? So and then you train the model, and then you tweak it, and then you uh, serve it and or put it in production. But that's a continuous process, right? Because it keeps learning from the data. So that's the more data you have, the so yeah. So
Well,
it's just like not a one time thing, right?
it's not a one-time thing for a couple of different reasons. You may be just tweaking your model to try to make improvements, but in a lot of cases, the model needs to model parts of the world, and the world changes.
Mhm.
So, for example, if you're working in fintech, if you're trying to model markets or risk scenarios or what have you, those things change constantly, like day by day. So you got to be constantly taking in new data and training your model to work in today's reality. Um, and it depends on what you're doing. I mean, if what you're trying to do is recognize the difference between a picture of a cat and a picture of a dog, that probably doesn't change too much.
Yeah.
At least I don't know, maybe yearly or something. But but other things require a much more frequent updates and just like with people, understanding the world, you kind of need to update yourself. Um, but there's also just trying to tweak the model either to make it more efficient and more cost effective, or because you see problems in performance in particular areas, or just overall you think that maybe a different approach would generate a better result or what have
Mhm. Yeah, there's also another question that has come up lately about the bias of your model and or the how reliable your model is, um, or maybe objective, right? So I think that's a kind of interesting topic, where some of these models, they detect, racially different people different way, for example, right? So some of the things that I've read about.
you. Yeah, well, that's an important topic.
Yeah.
Um, it's important for a number of different reasons. So um, you can easily have bias in your model. So meaning, I mean, it's easier to see in cases when you're talking about people, but it could be anything really.
Yeah. Yeah.
But with people, you could recognize, or your model could work better for some people than others, and based on different characteristics. So it could be racially, racial characteristics, like you recognize. Suppose you're trying to recognize faces. You could recognize faces of one race better than another. Um, it could be geographically or by language. Maybe you understand one language better than another.
Right.
Well, that's it's an important problem for that reason. It's also important for just understanding different sets of customers. So you could have customers that are shopping for a particular part of your product line, and you're trying to do recommendations, and your model may not work as well for that part of your product line as for a different part. And you, as a business, want to understand that too. So what that means is you need to do what we refer to as deep analysis of your model performance, and not just surface level or top level analysis. So what that means is, rather than just taking all of your data and generating one number to represent the accuracy or however you're measuring your model performance for your entire data set, you need to slice your data for different parts of your domain. So if your domain is recognizing people, then you slice for different races or different geographies or different languages. If it's products, then there's different parts of your product line. And for each of those slices, you measure performance.
Got it.
So when you have slices where your model doesn't perform as well, you at least become aware of that.
Right.
And then, now that you have to do something about it. And so there's different ways to approach trying to fix that. You can try to get more data, just more examples in those particular slices, which is kind of the basic starting point of how to do that. There's other ways to do that too. Different model architectures are more tolerant of different slicing, so they have less bias.
Hmm.
Actually, what that means is they generalize better. Things like lattice model architectures. You can also reweight your data so that where you may have fewer examples in a particular slice, they're weighted more heavily.
Hmm.
You can try to do data augmentation where you synthetically create examples for particular slices. There's a number of different ways to try to deal with that. But the starting point is to actually become aware of it and measure it.
Hmm. Are there any future plans for TFX to have some sort of enhanced capability to help with that, or
Already does.
already does it?
Already does. Yeah. So there's one of the libraries that we kind of blew past earlier. TensorFlow model analysis enables that kind of deep analysis of your model's performance.
Okay.
And then the evaluator component, which is one of the standard components that comes with TFX,
Hmm.
is used to run TFMA, TensorFlow model analysis, in your pipeline. So by default, every pipeline should have that capability, and then it's up to the user. They have to apply their knowledge of the domain that they're working in to know which slices are important, right? So they have to understand their application and what they're trying to do. And then that becomes part of how they set up the evaluator component in their pipeline.
Right.
But they can also do it offline too, just with TensorFlow model analysis, if they want to take that result and work with it offline, maybe in a notebook or something.
Okay. So so they could either do it manually by doing that analysis, taking their time, or there's also mechanism to do that, to feed that back automatically into the pipeline if they need to.
Yeah.
But there may not
You
be
know,
any guarantee because it's still computers, so the human factor may not be there, right?
well, you do have to configure it with the slices that make sense in your world,
Yeah.
right?
Okay. Yeah. Yeah.
But once that's set up, that becomes part of what we call model blessing.
Hmm.
So at the end of a pipeline, you've trained a model, and then you want to measure the performance of it. That's where we're going to use that kind of deep analysis. And then there's a question, because usually you already have, unless it's the very first time you're running it, you already have a model in production. So the question is, this new one, is it actually better than the one that you already have?
Hmm. Hmm.
So there's a comparison that's done.
I see.
And if it's actually better, then this new one is promoted to production. And that might mean pushing it to a canary deployment or what have you.
Right, right.
But if it's not better than what you already have, you don't want to push it. And these things are set up to be automated processes. So
Hmm.
you don't want someone to have to check every time you run, a training pipeline.
Right.
You want to define that and have it run automatically, and then you audit it periodically.
And then you set up those comparison variables, right? Or the comparison parameters, right? So, and those may vary between different fields and what type of model or you're training, correct?
Yeah. So the data that you have, uh, you need to figure out uh, what part of that data to generate slices on. So,
Hmm.
for example, if it was data about products, then one or more of those fields, or they're in ML they're called features, uh, would be what you'd slice on. So maybe it's a product line number, say,
Hmm.
or something, a SKU number. I don't know, whatever it is. For geographies, it would be that. For races, assuming you actually had that in your data, um, because if you don't know, if your data doesn't express things, then there's no magic. You can't.
Right.
Yeah,
It has to be there
it has to be there. Yeah.
Cool. All right. Well, this has been great and a very interesting conversation. And so does the TFX project work with any foundation, or they are only independent, or just Google is just the main sponsor, or there are a lot of other organizations working on it?
So TFX is an open source community, and there's a special interest group that focuses specifically on creating add-ons for TFX, because we have a number of layers where we're open and people can create community contributed add-ons, but we also accept PRs from the community and so forth.
Hmm.
Beam itself is part of the Apache Foundation, so that's why it's Apache Beam. so
Yeah, yeah.
so that's but we're not like TFX or TensorFlow. They're not like Apache projects or anything
Yeah.
like that.
Okay. Yeah, I mean, this is the tag runtime part of the CNCF, so I'll just leave it open. So if there's anything that the CNCF can help out, as a foundation, feel free to reach out, basically. So,
Well, so one thing to be that would be interesting to understand is, for cloud-based deployments, um, there's a couple of different ways that we work on a cloud. So if you're using, say, Airflow, you could deploy in VMs on a cloud, and set up your own uh, compute resources to run those nodes. You could run in a cluster in a Kubernetes environment.
mhm.
Uh, but I'm wondering, are there other cloud native execution environments that we should be looking at other than, Kubernetes, or just kind of basic, VM style? I'm thinking of things like Mesos, for example. Um,
Yeah, yeah, I think this Mesos is not very active anymore. So don't I think Kubernetes basically has taken over for the container orchestration as a standard.
mhm.
Um,
What about Nomad?
Yeah, Nomad is another one. So yeah, that's another interesting one from HashiCorp. So that's another one that could be,
Nomad from HashiCorp.
yeah. And then there's also the cloud providers. Yeah, I mean, you work at Google, so Google Cloud has this different ways like Cloud Run, but AWS is also, you know, or they come out with products like Fargate, and that allow you to run just the container or the pod in an on-demand way, the Kubernetes pod in an on-demand way, pay as you go. Um, so maybe it's more efficient, more cost efficient for people who just want to run the maybe batch pipelines or some of these workloads in batch.
Is
Uh,
that is that essentially Kubernetes or?
yeah, it is Kubernetes under the hood, but it's they have it in a way that allows you to do more like a serverless pay as you go. Um, yeah,
Okay.
and then yeah, there's also serverless, but I mean that's a whole different uh, area, I think, because I mean the way that you will have to create functions to run your orchestration, so it will be changing a lot of different components, I think. So.
Robert, is there a managed TensorFlow offering that you've come across?
Yeah. So we managed TensorFlow. That would probably map to TensorFlow Enterprise, which is one of the offerings from Google Cloud. There's also managed pipelines, so TFX pipelines, which that's the Vertex AI pipelines offering from Google Cloud that's also managed. So, it's a managed service. And that's, for the distributed processing side of things, that would be Cloud Data Flow, which is a managed service. Uh, that so I mean, you can set the whole thing up as a managed offering. And in fact, from Vertex, you don't even see the other services that it's using. It just handles it all in one managed service. I mean, you could dig into them, but you're not managing anything.
Sure, no, definitely. And I guess depends also on the size of your team and I guess where you want to, as a company, put your efforts in.
Yeah.
Earlier, you were mentioning, comparing different learning models, and I'm wondering with TensorFlow Hub, is that something that happens with those models between the different categories that are offered there?
You mean, is the performance of those analyzed?
Yeah, and just like
Yeah,
compare against each other.
it is, but keep in mind this is going to be specific to a particular data set. So you can take those models and reuse them, but you're going to use them with your data. So it's really an aspect of how well it performs for your data, right? So that's why you don't just take it and run it off the shelf. You almost never do that. Usually you're going to take it and you're going to do transfer learning to fine tune it for your data. So for example, if you're doing text processing and trying to understand, maybe customer queries for a chat bot or something, you might use something like BERT that you're going to pull from TensorFlow Hub as a starting point. But then you're going to give it your data set and you're going to fine tune the training of that model, which essentially just means continuing its training. So it's you could think of it as it's graduated from high school and now you're going to give it college. so um, so that's how it's going to learn about your data, and the bias is going to be in how well it works with your data. Um, so so that's an important thing to be aware of.
Sure, absolutely. And thank you for that distinction. And so I guess like you were mentioning, you do the training more so locally. So that's like one of the more, common patterns that, you'll take one of those existing models, I guess, train it with your data specifically. And then once you feel like it's, I guess at a good state, use something like TensorFlow or extend it to just be able to run it in production.
Okay, no. So you're going to take that model, you're going to train it, or you're going to fine tune it. You're going to continue to train it. It's called transfer learning. That's done in the TFX pipeline. At the end of that pipeline, you end up with a trained model. So this is a model that's been trained for your data. Then you're going to take that model, and that's what you're going to put into production to generate predictions. So the TFX pipeline, except if you're running in a batch, but typically most people use TFX most of the time for training. So that's where that would get used.
Gotcha. Sorry about that confusion.
Yeah. Yeah, no, that's a lot of people are, just trying to wrap their head around it.
Yeah. Then for serving, you what do you use for serving? Do you have the different mechanisms that you can plug in?
Yeah, so those are those deployment targets that I talked about earlier. You could have a server or server cluster that runs TensorFlow serving, or it could be running NVIDIA Titan, or you could have a managed service like Vertex AI Predictions, or wherever the equivalent is on AWS, I forget, or Azure.
SageMaker.
That's where you're going to do the serving, or you could be doing it just in a mobile app on your phone, or you could be doing it in a web browser. So you could just deploy the whole thing into a web browser, and nothing runs on your server.
Does hardware have a strong impact? I imagine the answer is yes, but I've noticed that we've gone from using like GPUs. I think Google has TPUs, and then it seems like FPGAs might be also an area that is being explored for machine learning.
So that whole class of things we talk about accelerators. So you can always do your training, and it's typically the training that takes the most compute resources. But other parts of things do too. I mean, feature engineering can take a lot of compute too. Typically, that's you can do all of that on a CPU, but it's faster on an accelerator. So either a GPU or a TPU or FPGA or whatever. If you want to speed up your training, then those become important. Now the challenge there is that they often have a lot less memory, and they tend to be data hungry. So you want to keep them busy. You want to feed them as fast as they need to be fed. And you want to stay within, the memory that they have on board. But these are all pretty well understood at this point. I mean, there's well-defined tools for doing that. The other part of that is just distributed training. So if you're going to distribute the training of a single model across multiple compute resources, you have to organize the way that models are updated during the training process. So there's a number of different algorithms that are used for training models in a distributed fashion, and each algorithm has its pluses and minuses.
Yeah, I think this is a really good use case for edge computing training, something like when maybe you have some sort of a survey mechanism at the edge, but then you may want to get some training out of that data that is coming in and feed it back, right? So, and maybe you can, so then and have some distributed mechanism for retrain the model.
Yeah, there's so we talk about federated training. There's that. Usually for edge cases, so we do a lot to think about, like device limitations for really constrained devices, like beyond a mobile phone. I mean, mobile phones are pretty powerful these days, but like a microcontroller,
Yeah.
if you're trying to deploy a model, we can deploy a model onto a controller with as little as 20K of memory. And if you think about 20K, I don't know when the last time you read anything in 20K, but it's been quite a while since I've run anything in 20K.
Yeah.
So to do that, there's a lot that you have to do to really optimize your model. And there's things like quantization and pruning and knowledge distillation that are used to really optimize that model for those really tight environments. I mean, on the other side of things, you could have latency requirements too. So you need to generate a prediction in 5 milliseconds, things like that. That all those optimization issues are really the difference again between maybe just like doing some research and writing a paper versus actually doing a product or service.
Got it. Yeah. Oh, I think we're out of time. It's like already nice, but yeah, thank you very much. This has been very, very informational and very interesting. So I hope we can keep in touch. And yeah.
Great. Well, my pleasure.
All right.
I should stop sharing, right? I'm still sharing. Yeah.
Definitely
Okay.
session. Thank you so much.
Thank you.
Yeah. Thank you.
Okay. Bye-bye.
Bye.